From 2Keto LLC, it's the Obesity Code podcast with Dr. Jason Fung and Megan Ramos. Each week, we bring you lessons and stories from the Intensive Dietary Management Program in Toronto, Canada. I'm Carl Franklin. And on the show today, energy balance. The Obesity Code podcast is brought to you by 2Keto LLC, who strives to support the low-carb community with podcasts and other publications. Today's show is a bit different in that we're not telling a patient story. Instead, we're going to let Dr. Fung talk as much as he wants about energy balance, the calories model, and the hormonal model of obesity. Normally, when we put this show together, we get the patient to tell their story. Richard Morris explains some of the science, I chime in with some narration, and Dr. Fung, Megan Ramos, and other experts add their thoughts about what the patient might be dealing with. Typically, Dr. Fung sends us an extended explanation, but we end up using only the key parts of it to keep the story going. But these recorded bits are, by themselves, fascinating. So we thought you'd like to hear one of them in its entirety. So this episode is dedicated to the idea of energy balance, the calorie model versus the hormonal model. And it starts when Richard was listening to a lecture by Dr. David Ludwig.
Hi, I'm Richard Morris, one of the 2Keto dudes. Last year I went to a presentation in Sydney by Dr. David Ludwig, Professor of Pediatrics at Harvard Medical School and Professor of Nutrition at Harvard School of Public Health. He said something interesting.
The standard approach to weight loss, as we know, is based on the notions of calorie balance. Calories in, calories out, so just eat less and move more. It sounds really simple, just one problem. It doesn't seem to work for most people over the long term.
The problem is that we tend to think of human energy use as a simple linear equation. We put energy into the system as fuel, we take energy out of the system as exercise, and the balance is then stored as fat.
The calorie balance notion is correct from a physics standpoint, but humans aren't toaster ovens. For an inanimate object, the calories in and the calories coming out must balance. But humans respond dynamically to calorie restriction. So when you put fewer calories into the body, we know that hunger increases, but more fundamentally, metabolism slows down. And that's going to antagonize weight loss.
This is an interesting problem. As we eat less, our bodies reduce our metabolic rate, so they use less energy when they're just sitting still, apparently doing nothing. If we decide to run on a treadmill, we just get more hungry. Mathematically, this is referred to as a complex system, where the outputs feed back into the inputs of the function.
The first law of thermodynamics says that within any closed system, the energy remains the same. That whatever you put in is available to take out. And in humans, if you put in energy and don't take it out, it stays primarily as body fat. So there's nothing wrong with that equation from a scientific perspective. It just doesn't tell you very much about how to approach obesity. Let's take the example of fever. You could think of fever as just a problem of temperature in and temperature out, right? So from that perspective, you could suggest that someone with a fever just get into an ice bath. And it's going to suck heat out of the body, and it'll break the fever. Now, of course, that will work if you could convince someone with a fever to get into an ice bath, but you probably couldn't. And if you could, they're not going to want to stay in that ice bath very long. Why? Because the body fights back. With severe shivering, blood vessel constriction, and you'd feel miserable. Alternatively, treat the cause of the fever, such as with a drug like aspirin, and you lower the body temperature set point. So then what happens is you want to be cooler. You throw off your clothes, you sweat, and your temperature comes down without the struggle. And the same thing is true with obesity. You lower the body weight set point by changing the type of diet we're eating, not how much. You lower the body weight set point, And then you lose weight with your body's cooperation, not with your body kicking and screaming.
Dr. Ludwig referred to a study by Rudolf, Libel and others in 1995 that attempted to explain this idea of a body's set weight, which our bodies attempt to defend when we try to lose weight. The study took 18 obese subjects and 23 subjects who had never been obese. They were all studied at their usual weight and after losing 10% and 20% of their body weight by underfeeding, or gaining 10% by overfeeding. They found to maintain a weight loss of 10% of body weight, the subjects who had never been obese saw a drop in total energy expenditure of around 6 kilocalories for every kilogram they had of fat-free mass. The obese participants saw a metabolic slowdown of 8 kilocalories for every kilogram of fat-free mass. Now, subjects who gained 10% of their body weight saw an increase in total energy expenditure of 9 kilocalories per kilogram of fat-free mass if they'd never been obese, or 8 if they had been obese.
Which brings us to Jason Fung's commentary today, which we will play in its entirety. Here's Dr. Fung.
So what does this study really show to us? And one of the things is that obesity is not merely a caloric issue, because everybody responds very, very differently to different calories. So when you're trying to make somebody gain weight, it's assumed to be very simple. You just tell them to eat whatever they want and they should gain weight. And this is what almost everybody thinks, but it's actually not quite as simple as that. So in the 1960s, there were some very famous studies done by Dr. Ethan Sims where he wanted to make people gain weight. He asked the very simple and sort of counterintuitive question, can I make rats gain weight? And what he found was that it's actually very, very difficult to. When they have studies on obesity, for example, they don't take normal mice and give them access to whatever food they want and watch them as they get very fat. Because when the mice have access to as much food as they want, they actually stop eating when they're full. And any attempt you make to force feed them is sort of futile. And this gets back to the point that there's a body set weight. This is also called the apostat, which is that when you have a certain body weight, so the mice have a certain body weight, if you try to make them obese, simply by giving them access to food, they will stop eating when they're full. And this is because the body has a sort of feedback mechanism where it senses that it's getting too fat. So when they eat, insulin goes up, fat cells grow. Fat cells, as they expand, secrete leptin. Leptin then acts on the brain, tells you to stop eating because you're too fat. And this is a very good mechanism, because if mice get too fat, they're going to get eaten. And they're not going to be able to go out and escape or run or do any of the things that they need to survive. The thing is that this is a normal mechanism for the mice, and it's actually a normal system in the humans as well. When you have experimental mice who are obese, these are not normal mice. They don't take normal mice and give them food because they'll stop eating. And you can't make them obese. You try and force feed them, and then they will just stop eating, for example. So you can put the intravenous into them and give them nutrition, and then they'll simply not eat until they get back to their normal weight. So when they do experiments on mice who are obese, they're actually genetically bred to be obese. So there's something there that is very powerful, which is stopping us from becoming obese. And it's this sort of leptin pathway that's really, really important. Obesity is predominantly due to leptin resistance because the leptins can't tell us to stop eating. So the sort of revolutionary thing that Ethan Sims did was that he then asked the question, well, I can't get mice to gain weight. Can I get humans to gain weight? So he went to the local college, which was in Vermont, and he said, okay, I want a bunch of college kids, and I want you to gain a lot of weight in a short period of time. So he thought, and everybody else thought, this would be like the easiest thing in the world to do. They're just going to eat a whole bunch of stuff, they're going to get fat, and there you go, experiment done. Turns out that it worked very poorly. The college kids would gain a bit of weight, and then they simply wouldn't gain any more. And almost no matter what you did, they couldn't gain weight. So, kind of puzzled, Dr. Sims then went to somewhere where they couldn't refuse him quite so easily. He went to the Vermont State Prison, and he made some of these inmates gain weight. So what he did was he initially raised their food consumption to 4,000 calories per day. And some gained a bit of weight, but then they stabilized. So he kept telling them to eat more and more and more. The thought was that perhaps these inmates were simply exercising it all off. So he had people in the prison that would watch them eat, make sure they ate all their calories, and also made sure they didn't increase their physical activity, because he thought these college kids were simply, playing some more sports, and then that's why they weren't gaining weight. And once again, some of these people were eating up to 10,000 calories per day in order to gain weight. And it would take 4 to 6 months, but eventually they did increase their weight by just making them eat more and more and more food. And one man, he gained less than 10 pounds. I mean, eating 10,000 calories a day and having only a 10-pound weight gain. So the question is, how can that be? Well, the only way that can be is that the body's own metabolism has ramped up to such a degree that it is simply burning off all of these calories. So remember that we're not trying to deny the first law of thermodynamics. When you eat food energy, which is calories, you have two choices. You can store it or you can burn it. If you burn it all, you simply won't gain the weight. The erroneous assumption in the sort of calories model is that calories out, the basal metabolic rate, stays stable, but it does nothing of the kind. And in response to overeating, it simply the body burns off all these calories and maintains that weight that you set. So what happens is that these people eventually gain weight, and then what happens when they stop? So the experiment's done, 6 months, they've gained like 20% of their body weight, 50 pounds or whatever. And then you stop the experiment, what happens? Well, in virtually all cases, all these people went right back to their initial body weight. So you see that you can do it in the short term. You can force things through the short term, but in the long term, this does not happen. And this is an experimental condition. So it's very difficult to make people fat. So what it demonstrates, these overeating experiments, is one is that calories in, calories out simply does not explain it, because remember that if you think that the energy in is the main problem, then you assume that the energy out is staying relatively stable, but it doesn't. In fact, the metabolism increases by a tremendous amount. It had increased by almost 50% in an effort to burn off these calories. And the second thing that it really demonstrates is sort of the time dependence of obesity. So in the time dependence of obesity, people who have been obese for a long period of time have a lot more trouble losing weight than if you've been obese for sort of a few months through some experimental condition. But once again, the calorie sort of theory says that it should all be the same. So somebody who's been obese since childhood, for example, for 40, 50 years, should lose weight at the same rate as somebody who's been obese for, 4 months. That's what the calories theory would predict. But of course, it's completely untrue. So the people who have obesity, who simply became obese for that experimental condition, well, they lose that weight really, really simply. It goes down like it doesn't even take any effort. And the people who have obesity for a long period of time, it just stays high, and it really takes a lot of work to bring that down. So clearly, if you've put your set weight to a high level and it stays there for a long time, well, it's going to be harder to bring it down. If your set weight never really moved because you only did it for 4 months or whatever, as in these overfeeding studies, then what happens is that everything goes down very quickly. And how do you explain this? Well, again, it's very simple to understand once you realize that obesity is a hormonal problem of insulin resistance and leptin resistance, and not simply a sort of calories problem, which predicts that, well, losing weight is going to be the same for everybody. If you think about resistance, the phenomenon of resistance is that whenever you have a hormone and you keep it high for a long period of time, then the hormonal receptors get desensitized to this. Then they stop working. If you think about it, this phenomenon, it happens in everything. So if you listen to loud music, for example, for a long period of time at a very high level, then your ears become a little bit deaf. And these are protective mechanisms. So your body is trying to protect its hearing. If you're exposed to bright light for a long period of time, well, then you adapt to it by, your pupils constrict and so on. Then you go into somewhere dark and then you're disconcerted. You get adapted to that. And then when you go into the bright light again, it's very bright and you lose that adaptation. But this is the point. Any stimulus, when it's taken for a long period of time, is going to produce resistance. The example I sometimes use is the boy who cried wolf. So in that story, a boy cries wolf, and the villagers come running. If he cries wolf every single day, well, pretty soon the villagers see that nothing is wrong and they stop coming. That's resistance. They've become resistant to his cries because they hear his cry, but they don't respond the same because they know that nothing is wrong. That's the same thing with the hormones. Hormones have the same sort of phenomenon. If you stimulate insulin all the time, you're going to get resistance. If you stimulate leptin all the time, you're going to get resistance because this is a normal phenomenon of biological systems. In the body, hormones never do this. They're supposed to be pulsatile. So you can look at hormones such as parathyroid hormone, thyroid hormone, growth hormone. They're not high all the time. They go high and then they go very, very low. So if you look at, say, growth hormone, you get a real spike and then it goes down virtually undetectable levels and that stays down for most of the time. So again, if you think about being in a dark room and you suddenly get exposed to a little bit of light, you can see it because you're so used to the dark room. As opposed to if you're in the bright sunlight and then you get exposed to a little bit of light, you can't see it because you're not adapted to it. So what our body does in essence is keep us in a dark room all the time. That is, levels of light are very low, and then you get a little bit of light, you can see it immediately. So in hormonal levels, you get almost no hormone levels and then a sudden kind of spike, maximum effect, and then back down to zero. That's the way it works. Where things break down is when you start to have hormones that are high and stay high because then the body becomes resistant to it. If your leptin level, for example, goes high and stays high, you're eventually going to develop leptin resistance, which is the problem that you see in obesity. It's not that these obese people don't have leptin. It's that they have lots of leptin and it's high all the time, and therefore the body has sort of lost sensitivity to it. It's, leptin's crying wolf all the time, so the body simply stops responding. And it's a time-dependent phenomenon. So the longer you're in this state where hormones are high, all the time, the deeper your resistance. And that explains a lot of the problems that you see in obesity, which is that it's simply the longer it goes, the worse it is. The other major hormone that we talk about for obesity is insulin. So insulin has the same problem. So if insulin is high all the time, you're going to develop insulin resistance. If you develop insulin resistance, then your body responds by producing more insulin. But you see how it's a vicious cycle, because high insulin leads to insulin resistance. Insulin resistance leads to high insulin. And it's just going to go round and round and round as things get worse and worse and worse. So think about it this way. If you listen to headphones and the music's a little bit too loud, well, you get a little bit deaf. Then you turn up the volume. But the turning up the volume was what caused the problem in the first place. So you get a bit more deaf. Then you turn it up and you turn up the volume, get a bit more deaf, and it just keeps getting worse and worse. And the longer you spiral in this vicious circle, the worse it becomes. So the solution is not to turn up the volume. The solution is to turn down the volume. It's not to turn it down, but keep it steady. So in the case of the boy who cries wolf, the solution is simply to stop crying wolf. It's not to cry wolf, but softly all the time. You got to stop it completely. Let the levels go down as much as you can. So let the insulin levels go down, because remember, it's a war between insulin and leptin. Insulin's trying to make you gain fat. Leptin's trying to make you lose fat. But eventually, because leptin resistance developed, you get this loss of control. And because of this loss of control, leptin, which is really one of the controllers of the body set weight or the apostat, your kind of body set weight keeps going up and up and up. And it's controlled by this state of insulin resistance, the state of leptin resistance. So getting back to insulin and insulin resistance, because this is the cycle that is so important to the time development, the time dependence of obesity. Which one comes first? Is the problem too much insulin, which is called hyperinsulinemia, or is the problem insulin resistance? Well, luckily, there are studies that have looked at this exact question.
The study Dr. Fung refers to is called Early Changes in Postprandial Insulin Secretion, Not in Insulin Sensitivity, Characterized Juvenile Obesity. Diabetes 43, 696 to 702, 1994, by Lestunf et al.
What they did in this study, they looked at juvenile obesity, so relatively early onset obesity. And what they wanted to know is the problem primarily too much insulin, hyperinsulinemia, or is the problem predominantly insulin resistance? So as they measured these juvenile obesity cases, what they found was that in the plasma insulin level is high whether you've had the obesity for a very short period of time or a longer time. The non-obese people had low levels, but insulin resistance kind of keeps going up and up with the duration of obesity. That is to say, if you developed obesity relatively soon, your insulin resistance hasn't gone up yet, even though your insulin levels are high. So it's time dependent once again. The longer you have the obesity, the more you have this insulin resistance. So the primary effect is not the insulin resistance, because at sort of time zero, the insulin resistance is low. It's the hyperinsulinemia. So what the primary problem of obesity is, the root cause of the obesity in many cases, is hyperinsulinemia. Which is very powerful, because when you formulate the problem as a problem of hyperinsulinemia, the solution becomes obvious, because the solution of too much insulin is to lower insulin. That seems pretty obvious. But if you have a lot of insulin resistance, then it's going to take a lot more time to lower the insulin levels because of all that insulin resistance. It's a time dependent. So the bottom line is this explains how it is that we have this sort of time dependence of obesity. If you've been obese for longer periods of time, it's going to be harder for you to lose weight. You've had more time for the insulin resistance to develop. You've had more time for the leptin resistance to develop, and it's just going to take time for that to get better. So knowing this is very powerful because then it avoids this sort of blame. These people who say, oh, well, I was obese for a month and a half and I lost it all. So should you, even though you've been obese for 40 years. It's not fair. Because the people who have been in that sort of state of obesity have had a lot more problems losing weight, and it's not really their fault. That's just the nature of the problem. And this really is a cautionary tale because with this sort of epidemic of childhood obesity, we're actually in for a heck of a time because these people who are gaining weight as children are going to have a lot harder time when they're 40 years old trying to lose weight. And one of the things that's really interesting is that we've seen obesity rates explode in children as young as 6 months old.
The study Jason's referring to here is Trends in Overweight from 1980 to 2001 among preschool-aged children enrolled in a health maintenance organization. Kim et al., Obesity 15, 2004.
And what they looked at was obesity in 6 months old, because in children who are 6 months, what they eat and what they do is very standard. That is, they eat to satiety breast milk, and in some cases formula, and they don't move because they can't. They just lie on their backs all day. So if you follow a sort of calories in, calories out model, you'd say, well, calories out is stable because they're just lying on their backs all day. They only eat sort of one food, which is breast milk. Well, how is it that we're getting so much more obesity? We have triple the rates of obesity in the 6-month-old compared to 20 years ago. And the answer to this, of course, is that they're being exposed to much higher levels of insulin in the womb. If you have mothers who are overweight, they have too much insulin. That insulin is going to go to the baby, and they're getting exposed to all this high insulin in the womb, so they're going to be heavier at the start, they're going to have more insulin resistance, and they're going to have more obesity.
It's actually not a direct relationship between the maternal insulin of the mother and the fetal insulin of the baby. Glucose itself is just a small molecule that easily passes across the placental barrier from mum to baby. So if mum is awash with glucose because she has insulin resistance, then the baby is also exposed to massive amounts of glucose. Insulin, however, is a very large molecule. It's roughly 30 times the mass of the glucose molecule, and there is evidence that human insulin does not pass the placental barrier. So if mum has a lot of insulin, baby doesn't get that insulin. The baby's developing pancreas has to learn very quickly to make adult loads of insulin.
So in essence, this is a problem that keeps getting worse because as you have an obesity crisis which affects childbearing women, they're basically marinating these children in insulin from the time that they were conceived. And then they're going to have a lot more trouble with childhood obesity, and then eventually adult obesity, and so on and so forth down the line. And again, the sort of calories model just doesn't explain it, but you can understand it by going to a hormonal model of obesity, which clearly is much more physiologic. Now to get back to the Rudy Libel study, if you look very closely at the data, there's two very interesting things. So remember in this study, they took volunteers and they essentially force-fed them to gain weight. When they did, then they asked them to go back to their original weight. And the people who are not obese took 4 to 7 weeks, but those who are obese took 6 to 14 weeks. In other words, double the amount of time. even though presumably they're doing very similar things because these are liquid diets. So even though they adjust the number of calories and the macronutrient composition is fixed, it's just much harder for obese people to lose weight compared to normal weight people. And that's something that everybody sort of knows about, but it simply doesn't jive with the current accepted sort of calorie model.
The RQ, or respiratory quotient, is a method of working out from the gases we breathe in and out which of our two primary fuels, glucose or fatty acids, we're burning. When we burn glucose, the complete oxidation equation is that we take 1 mole of glucose and 6 moles of oxygen gas, and we convert that into 6 moles of carbon dioxide and 6 moles of water. So if you look at the gas exchange at the lungs, for every 6 molecules of O2 going in, there are 6 molecules of CO2 coming out. It's a 1-for-1 ratio. So a glucose burner is said to have an RQ, respiratory quotient, of 1.0. Now, when we burn fatty acids, the oxidation equation is a little more complicated depending on which fatty acids that we're burning, but we produce much less CO2 for the same amount of O2. The ratio is roughly 7 CO2 for every 10 O2, so the RQ of a fat burner is around 0.7.
This respiratory quotient measures the amount of carbon dioxide, so it measures how much you're burning fat compared to how much you're burning carbohydrates. So on a standard diet, you can kind of get a rough idea if you're eating pure fat or pure carbohydrates, for example. So a respiratory quotient of 1.0 is sort of all carbohydrate diet, and 0.7 is roughly all fat diet. So, and in between there, you can see. So as you try to gain weight, as I said, it's actually much more difficult than most people imagine to do so in a short period of time. But when they measured the respiratory quotient as these people were gaining weight, they went from 0.86, sort of in between 0.7 and 1, so kind of a mixed diet, a bit of everything in moderation sort of diet, to 0.92, which is really mostly carbohydrate-based diets. So in order to gain weight, really the only way that people can do this is to consume a lot more carbohydrates. And again, this sort of makes sense because it's not calories, it's the insulin effect. Hyperinsulinemia is the cause of obesity. So if you want to gain weight, you need to eat more carbohydrates. It's as simple as that. And that's the only way that they could gain weight.
They were burning mostly glucose because they were overeating everything, but the insulin had prioritized the burning of glucose and the storage of fat.
When they lost the weight, they were not simply restricting their calories because the respiratory quotient measures just the macronutrient composition and not so much the total number of calories. But when they lost weight, the respiratory quotient went down to 0.78, which again is not that much higher than pure fat.
Now they were burning stored energy, so to do that, they needed to have their insulin go low to prioritize the burning of fatty acids.
So what they had to do, of course, is restrict their carbohydrates fairly significantly in order to get down to that level where they're able to lose weight, which makes sense again because if too much insulin is the problem with weight gain, as you eat more refined carbohydrates, you're going to gain weight. As you restrict your carbohydrates, you're going to lose weight. And experimentally, in fact, that's really exactly what they found, which is really sort of fascinating sort of confirmation of the fact that different macronutrients are going to have different effects on your weight gain despite being equal calories. When you're thinking about the problem of long-term weight gain or weight loss is, what we're generally concerned with, you have to understand that that problem is mostly tied in to an apostat which is set too high. That is, it's not about calories, it's about trying to crank this apostat back down. And the only way you can crank that back down is to understand what cranked it up in the first place. It's the insulin resistance, which is caused by too much insulin, and it's the leptin resistance, which is caused by the high insulin. So The root cause, though, is the high insulin, and therefore you have to get down to let's use strategies which lower insulin. There's no drugs that do that very effectively. In fact, just recently there was one class of drugs, which is the SGLT2s. They make you urinate out the glucose, but what was very impressive is that it causes weight loss, but sustained weight loss. So if you give this medication, you pee out, 300 or 400 calories a day of glucose, of sugar, your insulin levels go down and your body weight goes down and stays down as long as you stay on this medication. So people lose about 2 kilos of weight, but it stays down. And this is in contradiction to virtually every dietary study where it goes down for 6 months, then goes back up. So remember again that what we're doing with the diet is often reducing calories. The weight goes down, but then as the sort of apostat, this body weight kind of kicks back in, your body tries to regain that weight. And despite the fact that you're still eating less calories, your weight plateaus and then stabilizes. What's interesting about the medications is that, yes, they do cause a certain number of calories of loss in the urine, but it's really the lowering of the insulin that's effective for long-term weight loss, because you can restrict 300 or 400 calories per day in the long term and not have any sort of weight loss after about 6 months or a year, which is what was shown in the diabetes prevention study, the Women's Health Initiative. All these studies of calorie restriction initially have weight loss, but then after a year, most of the gains have dissipated. And here's the really important thing to understand is that all of these studies where they do these sort of calorie restriction, they see the initial 6 months of weight loss and then the plateau and then the weight regain. But this happens despite the fact that these people are still eating the lowered number of calories. So this sort of assumption that, people just went off the diet is not borne out by the evidence. The randomized control trials, the Women's Health Initiative, diabetes prevention studies, where they do as best a job as they can of measuring the calories and what they're eating, show that they're still eating fewer calories. But the weight is not going down. In fact, it's going back up. So it's not fair to blame these victims of obesity that, they just didn't have the willpower. That's not it at all. The fact is that this sort of cut your fat, cut your calories advice is extremely ineffective because you're not taking care of the root problem, which is the insulin. When you do take care of the insulin, this is what you find.
You've been listening to the Obesity Code podcast, lessons and stories from the Intensive Dietary Management Program. The Obesity Code podcast is brought to you by 2Keto LLC, who strives to support the low-carb community with podcasts and other publications. And you can support our mission by making a monthly pledge, no matter how small, at patreon.2keto.com. I'm Carl Franklin. We'll see you next time.